Hi everyone, I want to talk about natural forms of magnetism. The first kind is called ferromagnetism, from the word for iron. Ferromagnetism is really a property of a particular kind of material. It doesn't have to be iron. And is not a property in general of things. It's what's behind the classic bar magnet that we're used to. And it's a very strong form of natural magnetism, and fundamentally comes from the fact that internally every little atom is composed of an electron and a nucleus, and the electrons in the atom are in motion. Therefore, since you have charge in motion, each little atom has a magnetic field that's generated. In a sense, each little atom is a little bar magnet. And so, even though there's no net charge, each atom has a net magnetic moment. And so, each little atom is like a little bar magnet sitting there. And if you have another atom, they have a tendency to align with one another so that, these two are repelling one another right now. And what happens is that the north and south poles of those magnets have a tendency to cause it to shift like that, to flip around, right? It's kind of hard to show without these things falling over. But basically they have a tendency to twist in such a way that the magnetic moments are anti-parallel with one another, canceling one another out. The net magnetic field far away is essentially zero. Very similar to how positive negative charges basically shield the strength of the electric force. Same thing happens with these little bar magnets. However, there is a possibility for a quantum mechanical effect to come into play that actually makes it energetically favorable for the bar magnets to line up. When that happens, you have a net accumulation of a magnetic field and you have a ferromagnetic material. And so that's the ultimate source of that. It's a very strong form of magnetism, like I said, and that's about it. The second way in which we experience the magnetic force is with a bar magnet, or a horseshoe magnet like this guy. Stick it to the refrigerator. Now the refrigerator is not magnetic, but what happens is this source magnetic field actually induces a secondary magnetic field, much like how in the dielectric of a capacitor, a charge separation is induced by the presence of that external electric field. And so you have this secondary magnetic field which effectively is attractive and is weaker than the ferromagnetism we talked about, but this paramagnetism is still nonetheless useful for holding up pictures on the refrigerator and different things. Third form of magnetism is called diamagnetism. It's a little more obscure and really is based on something called Lenz's law, which we'll talk about in the next lecture, but that's fundamentally comes from the fact that the electromagnetic field does not like to change. And this almost a kind of inertia actually means that whenever there is a change in the magnetic field, there's kind of a counterbalancing magnetic field that comes into play that tries to oppose the change. And so this opposing magnetic field can actually be used to levitate things, and that's what this picture here is. There's actually a little video online where they're actually literally levitating this live frog inside this little laboratory experiment, and it's pretty cool. Of course, you don't see all the entire apparatus that's outside it that's constructed in order to make this phenomenon occur. So I don't think we'll be seeing any kind of levitating jetpacks in the future anytime soon. But who knows? Maybe that's something you guys will invent in the future. So those are the three basic forms of natural magnetism. And there is two other things I should mention before we take off. and that is kind of an artificial form of magnetism, the electromagnet. How does that happen? Where does that come from? Again, it's from this idea of circulating electric charge. Much like the atom is a circulating electric charge, we can create a situation like that with just wires and batteries, right? If we take a wire and create a circular shape of current, this is the shape of the magnetic field. It kind of creates like a donut shape around that ring. Remember, the magnetic field wants to be circular, and so basically you've got a circle around a circle. That's kind of a donut shape. That's what this picture represents. Now that's not quite the electromagnet we want, but if you take, instead of a ring, a spiral, then that magnetic field gets trapped inside. It can't cross through the spiral, but it gets trapped. It wants to be circular, but it's trapped into basically these straight lines, and that is the form of the magnetic field that comes out of a bar magnet. So charge in a spiral, current in a spiral will create a magnetic field very similar to a bar magnet, and that's exactly how electromagnets work. And that brings our study of magnetism to a close.